Today we are talking about symmetry. Symmetry in relations, and that leads us to even and odd functions. So symmetry is another topic that I know that you have seen in Algebra 2. So this hopefully seems familiar to you today. Alright, symmetry. Consider a relation whose graph has the point AB on it. So you can, if you like, you can give these some numbers, like let's say that the point 3, 5 is on the graph of this relation. The relation has y-axis symmetry. If the point 3, 5 is on the graph, then the point -3, 5 must also be on the graph. So visually speaking, if the point 3, 5 is on the graph, then the point -3, 5 is also on the graph. There's that y-axis symmetry. Okay? Alrighty. The relation has x-axis symmetry if the point a negative b is on the graph. So if 3, 5 is on the graph, then 3, -5 must be on the graph. So here's 3, 5. The point 3, -5 must also be on the graph if it has x-axis symmetry. For origin symmetry, if 3, 5 is on the graph, then -3, -5 is also on the graph. So visually, 3, 5, -3, -5. There's origin symmetry there. I think of this as this point is reflected through the origin. Okay? All right. If you are given a graph, one way to determine y-axis symmetry is to envision folding the graph on the y-axis and visualizing, does that graph fold onto itself? Is it lined up? Is every point reflected through the y-axis? For x-axis symmetry, do the same thing except fold it along the x-axis mentally. You're not going to do that with your actual paper. You'll have all these folds all over your paper. It'll be a mess. But you can imagine doing that. Is every point reflected through the x-axis to another point on the curve? For origin symmetry, you can't fold it along the origin because the origin is a point. The x-axis and the y-axis are lines, so you can fold that. Can't fold it on a point. So you do need to consider this reflection. Is every point on the curve, does every point have the negative x value and the negative y value of that point also on the curve? Is every point reflected through the origin onto it itself, another point on the curve? Let's look at some examples of symmetry by looking at a graph. Okay, for this one, it does not have y-axis symmetry because there's a point here that's not over here. There's a point here that's not over here. Does it have x-axis symmetry? Yes, it does, because every point is reflected across the x-axis onto itself. Every point is reflected onto itself. Okay. Does it have origin symmetry? No, it does not. This point is not over here. So the only symmetry this one has is x-axis. Okay? For B, this one has y-axis symmetry because every point is reflected over the y-axis onto itself. Every point is reflected through the y-axis onto itself. It does not have x-axis symmetry. It does not have origin symmetry. So this one only has y-axis symmetry. Okay, this one. Well, this one has origin symmetry. Every point is reflected through the origin onto another point on the curve. Every point is reflected through the origin onto another point on the curve. Even these are reflected through the origin to another point on the curve. Okay, so that's what I'm looking at. Does it go through the origin to another point on that curve? Okay, does it have y-axis symmetry? No, it does not. If I fold this on the y-axis, it does not line up with itself. Does it have x-axis symmetry? No, it has only origin symmetry. Okay. What about this one? No y-axis, no x-axis, no origin. This has no symmetry. None of these three, anyway. None of these three. I could envision that this has symmetry with respect to some other vertical line, but not y-axis, x-axis, or origin symmetry. Okay, part number 2 here. Part of the graph of a relation is given. Complete the graph so that each type of symmetry is held. So for y-axis symmetry, every point on the curve I want to reflect over the y-axis. So this is the point -4, 1. I need the point 4, 1 to be on the curve. I go through and I find points that are there. This point is also here on the curve. So I'm going to go over here and make that point. This is already on the y-axis, so that's going to stay on my curve. Here's another point right here. So I'm going to go 2 over and 1 up. Yeah? And is there any other point? Yeah, this point is on there. -8, 5. So 8, 5 is on the curve. Anything else? I don't think so. This is close, but not quite. I think I'm just going to go and draw the curve from that. And then finish it up, maybe end about right there, like that. So that is y-axis symmetry. What about x-axis symmetry? Every point needs to be reflected across the x-axis this time. So this point is there, so that point has to be there. This point is here, so go through the x-axis across and get another point for that. This point is on there, so this point will need to be there. This point is here. It's 1, 2, 3, 4, 5 down, so 1, 2, 3, 4, 5. And then this is the point 0, 5, so 0, -5 needs to be there, and I can go ahead and draw it from here. X-axis symmetry. Origin symmetry. Okay, for origin symmetry we go through the origin to the other side. So here's this point here, through the origin to the other side. We'll bring it down there. Okay, here's another point right here. -4, 1. So +4, -1 needs to be on the graph. Here's a point, -2, 2. So +2, -2 must be on the graph. I'm going through the origin. You can see it. Okay, this point here, -6, +2. So +6, -2. This was the point -8, 5. So +8, -5 on the graph. So for origin symmetry, it's going to look like this. So that's how you would answer those types of questions. Before I leave this page, let me ask you a question. Function or not a function? This is not a function. It fails the vertical line test. If you have x-axis symmetry Could it be a function? No. X-axis symmetry will never yield a function. This had y-axis symmetry. Is this a function? Yes, it is. This had origin symmetry. Is this a function? No. It fails the vertical line test. So even though this has origin symmetry, it is not a function. Is this a function? It sure is. No symmetry, but it is a function. Okay? Function, not a function. This is not a function because of one point. It's not a function because of one point, and that is the point when x is 0. When x is 0, I get 2 y values. It's almost a function. We could make it a function if we put a hole right here. But as it is, it's not a function. Okay, what if you're not given the graph? What if you're given the equation? How do you tell if a relation has symmetry if you don't have the graph, if you don't know the graph, or if the graph is obscure, you don't know what the graph looks like? Okay? Well, to do that, to test for y-axis symmetry, you replace x with negative x and determine if your new equation is equivalent to your original equation. Determine if your new equation is equivalent to your original equation after you replace x with negative x. To determine x-axis symmetry, replace y with negative y. Do the same thing. Determine if your new equation is equivalent to your original equation. For origin symmetry, replace x with negative x and replace y with negative y. Then determine if your new equation is equivalent to your original equation. So let's go through a couple of examples. For y-axis symmetry, we're going to replace x with negative x. Replace x with negative x. So my relation is now 2y squared is equal to negative 1 over negative x plus 3. So now I'm going to manipulate this a little bit, see if I can force this equation to be equivalent to my original equation. I would have 2y squared. I have negative 1 over negative x. There's 2 negatives there. It makes a positive. Is this equation equivalent to that equation? No, it is not. So, not equivalent, therefore, no y-axis symmetry. Okay, what about x-axis symmetry? We're going to replace y with negative y. We'll have 2 times negative y squared is equal to negative 1 over x plus 3. Well, negative y squared is the same as, we're squaring the negative 1 and we're squaring y. So this is the same as 2y squared. Is this equation equivalent to that equation? Yes, it is. They are identical. Yes. Therefore, x-axis symmetry. And lastly, we're going to replace, we'll do origin symmetry. And for origin symmetry, we replace x with negative x and y with negative y, both of them. So I would have 2 times negative y squared is equal to negative 1 over negative x plus 3. This is 2y squared is equal to 1 over x plus 3. We already determined that that is not equivalent to our original, therefore no origin symmetry. You can, by the way, have more than one type of symmetry. So just because you find one that works does not mean you shouldn't keep trying to see if another one works as well. Let's do one more of these. Okay, here's our relation. We're going to test for y-axis symmetry first. And to do that, I replace x with negative x. If I replace x with negative x, I've got negative x squared is equal to 2 times negative x y minus 1. Well, negative x all squared is x squared, because it's negative 1 squared times x squared. That's just x squared, is equal to negative 2xy minus 1. Is this equivalent to what we started with? No. Therefore, no y-axis symmetry. For x-axis symmetry, we're going to replace y with negative y. So I'll have x squared is equal to 2x times negative y minus 1, which is x squared is equal to negative 2xy minus 1. Is that equivalent to our original? No, it's what we already said, that is not equivalent. Not equivalent. Okay? So no x-axis symmetry. Now we're going to test for the origin symmetry. To do that, replace x with negative x and y with negative y. We'll have negative x all squared is equal to 2 times negative x times negative y minus 1. This is x squared is equal to 2xy minus 1. Is that equivalent to what we started with? Yes, it is. Therefore, the only symmetry we have is origin symmetry. Okay? So it's a little work. That's how we do that. All right. Even and odd functions. A function is even when, for every x in the domain of f, f of negative x is the same as f. F of replacing x with negative x gives you back your original function. We did that when we tested for y-axis symmetry. We replaced x with negative x, and we got back our original function. So that means that a relation is even if it is a function and it has y-axis symmetry. Is it a function? Does it have y-axis symmetry? If your answer is yes, then your function is even. A function is odd if, when you replace negative x with negative x, you get negative y. Negative x gives you a negative y. So that is our origin symmetry. A relation is odd if it is a function and has origin symmetry. Remember, you guys, if you have x-axis symmetry, you do not even have a function. It is impossible to have x-axis symmetry and be a function. Can't do it. Even means y-axis symmetry. Even is y-axis symmetry. Odd is origin symmetry. Okay? Plus it has to be a function. Number 1. We know that this is a function because it's already in function form. F of x. Function form. And f of x is a single equation. I know this is a function. The question is it even, odd, or neither? So to find out, I'm going to replace x with negative x and see if we get back f. Or do we get back negative f? Okay? Well, if I replace x with negative x, I'll have negative x to the fifth minus 4x times negative x to the third plus 8. Okay? That gives me, what is negative x to the fifth power? Well, this means negative 1 to the fifth power times x to the fifth power. Negative 1 to the fifth power is still negative 1. So that is negative x to the fifth minus 4 times negative x cubed. This is a negative x cubed, which will make that a plus 4x cubed. Now we have plus 8. That did not change. Is this identical to what we started with? No, it is not. It's not identical, so it's not even. Not even. Is it the opposite sign of what we started with? So even gets you back same function. Odd gets you back the opposite, the negative of your original function. Is it the opposite of it? It is almost the opposite of it. Got that negative x to the fifth, got a positive 4x cubed. This blew it though. It's neither even nor odd. What if, before we leave this, what if we had the function just x to the fifth minus 4x cubed? What if that plus 8 was not on there? Then replacing x with negative x would have given us negative x to the fifth plus 4x cubed. That is the opposite of what we started with. So this is g is odd because it's the opposite sign. It's negative g of x. So g is odd there. But f, the one that we were given, is neither even nor odd. Neither one. Okay? Oops. Let's take a look at h over here. Alrighty. We're going to put in negative x for x. When I do that, I have negative x to the 2/3 power. Okay. 2/3 power means cube root, then square. Cube root, then square. If I cube root something, it's going to keep the negative. But then I'm going to square it. What happens to a negative when we square it? It becomes a positive. So this is positive 4x to the 2/3 power. When you square that negative, you get a positive, and you are squaring that negative. We got back what we started with. This is equal to h of x. Okay? H of negative x is equal to h of positive x. That means that h is even. It has y-axis symmetry, and it is even. Alrighty? Number 3. I'm not giving you the equation, I'm just giving you this graph. Even, odd, or neither? Well, this thing is not even a function. If it's not a function, it cannot be even or odd. This is not a function. Therefore, cannot be even nor odd. Or odd. Goodness, I've made too many videos today. I need to stop making videos. Alright, even though it has origin symmetry, it does have origin symmetry. It also has x-axis symmetry. It also has y-axis symmetry. It has every kind of symmetry. but it is not even or odd because it's not even a function. Okay, that is even and odd functions. And x-axis, y-axis, and origin symmetry.